Hello, welcome to this presentation about the RISC-KIT Hotspot tool. The RISC-KIT Toolkit consists of a number of different tools to look at coastal risk, and in this presentation we'll be talking about the fourth tool, the Hotspot tool. The purpose of a Hotspot tool is to compute the expected impacts of a storm event and to look at the effectiveness of measures that you can apply to reduce the impact, so-called disaster risk reduction measures or DRR measures. The Hotspot tool can be used in two modes. First of all, as a planning tool ahead of storm events. We use this then to look at the potential impact of storms, so for instance, where and when and how often might flooding occur at a hotspot site, and to use the tool to help assess and evaluate DRR measures in the hotspot. So for instance, would a seawall be effective in terms of flooding, or would it be more appropriate to use flood proofing? We can also use the Hotspot tool as part of an early warning system to predict the impacts of storms as they come. The Hotspot tool is typically applied on relatively small areas, say an area of interest of 1 to a couple of kilometers, and the tool is used to look at individual events, so on the time scale of say hours to days. The Hotspot tool computes impacts of storm events by transforming offshore hydrometeor conditions, such as oceanic waves and storm systems, to so-called onshore hazards, such as beach erosion and coastal inundation. These onshore hazards don't necessarily say anything about impact, though. To define impact, we need to know where the receptors are, receptors such as infrastructure, buildings, populations, natural cultural areas, and how these areas are affected by the onshore hazards. Finally, we compute the impact at each receptor using the prediction of the local hazard at the receptor and vulnerability relations. We can use the Hotspot tool to assess the effectiveness of DRR measure by comparing simulations with and without DRR measures. For instance, here we have two DRR measures, one a beach nourishment and the other as a rezoning. And we can use the Hotspot tool to simulate what would happen during one storm event for both these DRR measures. If we look at the results of the simulation, we see that the beach nourishment changes the way that the storm affects the coast. So the local hazards are different. There's no coastal inundation. Whereas the rezoning option, for instance, does not change the local hazards. There's an equal amount of beach erosion and there's still coastal flooding occurring. But both the beach nourishment and the rezoning reduce the impact, the number of receptors affected by the storm, compared to the reference case. The Hotspot tool consists of four main components, which we'll be discussing a bit more in the following slides. The first is a physics-based numerical model to compute hazards. Second is a Bayesian network to go from hazards to impact. The third is the Delft coastal fuse to manage model connections and early warning system data flow. And the fourth is a web viewer for dissemination of the results and to help in consensus building. The first component of the Hotspot tool are the physics-based numerical models that we use to compute the hazard at the hotspot site. So typically these models extend in a range from very large, covering an entire regional sea or maybe even ocean, and then scaling down to the smaller scale of the hotspot. Examples of the models that we use for these are, for instance, Deltares or RISC, going all the way down to detailed models like XBeach. The choice of models used in the Hotspot tool can be tailored to the specifics of the site. So for instance, the settings, the natural setting of the site, and the physical processes that occur there. But all models used in the Hotspot tool should be able to compute multi-hazards at the hotspot site itself. So for instance, erosion and overwash and flooding, to be able to compute the full coastal risk. In the RISC-KIT project, at a lot of sites, we use the X-Beach model to do this. This is fairly well validated for storm impacts on sandy coastlines. The second component of the Hotspot tool is the Bayesian network, which we use to compute impact, and I'll be discussing that in the next couple of slides. In the Bayesian network, we combine information about local hazards, like flood depth or erosion, and receptor information, like the locations of buildings, and vulnerability relationships, like depth damage curves, to compute the impact at receptors. The results of hundreds of model simulations with varying offshore forcing conditions, as well as varying DRR measures, are stored in the Bayesian network. And from this data set, the Bayesian network learns probabilistic relations between the offshore conditions, the local hazards, and the impacts at the receptors. This is an example of a Bayesian network, in which the various variables have been collected together in groups. For instance, the storm characteristics, like the peak storm surge and the peak wave height, and DRR measures, as well as local hazards, like inundation and erosion at the receptors, and the consequences or the impacts, so the damage to houses and risk to life. The advantage of the Bayesian network is that it's a fast, efficient, and interactive way of going through the data that's been collected. So, for instance, we can start to play with things like the storm characteristics. If we move to a particularly intense storm, then you'll see that the consequences change, the risk to life grows, and the damage to houses is increased. Another advantage of the Bayesian network is that it is fast to run compared to running a numerical model to compute the local hazards. So this means that the Bayesian network can be incorporated into an early warning system relatively easily. Another advantage there is that the Bayesian network provides a probabilistic result of the impact rather than a single deterministic result that you would get if you ran a process-based numerical model to compute the hazards and impacts. The third component of the Hotspot tool is the Delft coastal fuse that we use to manage model connections and data flow as part of an early warning system. An example of this as an early warning system is one of our case study sites in Portugal, the Rio Formosa and the Algarve, where there's a large-scale wind forcing model shown here that then provides input to a wave model for the Gulf of Cadiz and a tide model for the area of the Rio Formosa, and finally a hotspot model, X-Beach hotspot model of the hotspot site. The fourth component of the hotspot tool is a web viewer that we use to disseminate the model results and use as a tool to discuss the results and the effects of DRR measures in group discussions with stakeholders. So in conclusion, the Hotspot tool has four components: a set of physics-based numerical models to predict local hazards, a Bayesian network to compute impact, identify probabilistic relations between offshore conditions, local hazards and impacts, and to provide uncertainty ranges, Delft coastal fuse to run the numerical models in an operational forecasting system, and a web viewer for dissemination and data sharing. And we can use the Hotspot tool both as an ex-ante planning tool and to assess the effectiveness of DRR measures, and as part of an operational coastal flood warning system.